Okay, welcome back. I hope you enjoyed the practical. Quick question first, any questions about what we talked about earlier today in the first lecture? We were basically setting up some basic ideas and some notation. All right, I'm going to share my screen and pull up Hardy Weinberg, if I can. Yeah. And now where's it gone? Ah. It was there, now it's gone. All right, so Jerome, do you see that?
Yes.
Good, okay. So we're going to talk about Hardy, and I need to make this full screen, I think. Okay, so Hardy-Weinberg equilibrium is sort of a cornerstone of statistical genetics. Very old result, 1908. Hardy was an English mathematician who had a half-page paper in Science, and apologized for taking up space to show a trivial piece of algebra, he thought. Weinberg was a German physician who had a very long and nice paper about what we now call Hardy-Weinberg equilibrium and the biological ramifications. And so it's an important result, and it will serve to has its own intrinsic value, but it also serves to introduce several basic concepts for us. So Hardy-Weinberg law simply says that genotype probabilities are squares or products of allele probabilities for two alleles, and then as an extension to multiple alleles. And it's a law, it's not truth, it doesn't happen in practice, but it's a good theoretical result as a consequence of there being no evolutionary forces, no effects in drift or selection or mutation or so forth. It's a very good, if it's a result that we can use, it's a very good way of being able to replace genotype probabilities by allele probabilities. And it underlies almost all of the work we do in quantitative genetics. So why would it not hold? Well, the most common reason these days that is problems with the data. Our data sets are very rich now, but they also come with some noise. So an essential part of data cleaning is to check for Hardy-Weinberg equilibrium. There might be a population we're studying where there is inbreeding or some mating system which avoids inbreeding, and that will cause departures. We may be studying data from populations with structure, admixture. We may be studying data that's censored in some sense. For example, we might have a human data set of people who have a disease, and that can cause Hardy-Weinberg disequilibrium in genetic markers. Or we may see the results of natural selection. And during the debates of the 1960s and 70s, where debates between neutral versus selection theories of evolution, testing for Hardy-Weinberg was used by both sides of the debate to say their data were consistent with neutrality or their data were consistent with natural selection. So there's a lot of mechanisms which can cause departures from Hardy-Weinberg. We've already met a way of characterizing the departures with our inbreeding coefficient, the within population inbreeding coefficient. So, do you have a question? Yeah, so if you just mute. So we now see that F is really a way of measuring departures from Hardy-Weinberg. Hardy-Weinberg corresponds to F being 0. So that suggests what we might do is to estimate F and see if the estimate's significantly far away from 0 that we would reject the hypothesis. Problems with the data. there's a lot of reasons why we might detect departures from Hardy-Weinberg. Very often it's the case that heterozygotes are reported as homozygotes. And here's an interesting quote from Eric Lander, a very prominent geneticist in the US, director of the Broad Institute. And he said he was looking at some forensic data back in the late 80s and said to justify applying the classical formulas of population genetics in this particular case, Mr. Castro was on trial, the Hispanic population must be in Hardy-Weinberg equilibrium. In fact, Lander said that the data used from the testing company LifeCodes showed it is not. And when you apply a test of Hardy-Weinberg to the LifeCodes Hispanic data, one finds spectacular deviations, way more homozygotes, 17%, for example, than expected, 4%. Lander said this was not surprising, but he didn't realize at the time that the data was actually had typing errors, in the sense that heterozygotes were in fact recorded as homozygotes. So, but it's a good exercise to do the test to make sure that the data are, as far as we can tell, without error. A biological reason, population structure. Suppose we've got a large population we've sampled, and it consists of two subpopulations with no mating between them. In one population, the allele frequencies are 60-40, and the other, they're 40-60. If there's Hardy-Weinberg in each subpopulation, then here are the genotype probabilities, just the squares and products. If we did not recognize the subpopulation or ignored it and sampled the whole population, then we would find the two alleles, we'd expect to find them equally represented in our data. Certainly they're equally represented in the whole population. And if we take those total or average frequencies and apply Hardy-Weinberg, we find that we get an expected value of 0.25 for homozygotes, but in fact, the average of the real frequencies was 0.26. So both the homozygotes are more frequent in the whole population than we would expect from their allele probabilities. So these are just because in fact, our data consists of samples from two distinct Hardy-Weinberg populations with different allele frequencies. So that's a mechanism. With the same example, we can actually get a deficiency. So let me go back, the same example, but now let's imagine that there's random mating within each population and also between. So a random person taken at random from the whole has a 25% chance of coming from a mating between two people in this subpopulation, 25% of coming from a mating between two people in this subpopulation, and a 50% of coming from parents, two parents, one in each of the two subpopulations. You can work through the details, but it turns out that with that situation, and if the offspring are characterized by whether one or both of their parents was in population one, so the offspring of the hybrids, the between population matings, if those offspring are assigned to population one, then population two remains in Hardy-Weinberg equilibrium. And if we sampled that subpopulation, we would find Hardy-Weinberg. If we sample what is now called population one, but it consists of individuals with both parents in that population or with one parent only, then we'd find a deficiency of heterozygotes, of homozygotes, heterozygote excess. It's not huge, but it's not zero. So there are population structure issues that can cause departures from Hardy-Weinberg. And then, of course, there's the obvious ones like selection. If some genotypes are favored over others, that will perturb the genotype proportions. So how should we proceed with some data? The simplest thing is to take a sample and estimate the within population inbreeding coefficient. And we saw our maximum likelihood estimator for SNPs earlier. So we construct a test statistic, which is the estimate, the variable, minus its expected value, the true value, and the square root of its variance. If the true value is 0, or if that's our, if we hypothesize it's 0, so let's set f to be 0, because that's what we're going to test. Let's put f equal to 0 here. And then in that case, it turns out that the variance of the estimate is just 1 over the sample size, 1 over n. So we have f hat minus 0, the square root of 1 over n, and our quantity, our standard normal, is that. And if we square that thing, we get a number which is just, turns out to be the sample size times the square of the inbreeding coefficient estimate. So this is an easy number to calculate. And if everything is correct, if really was 0, so this really was the mean, and this really was the variance, this would have a chi-square distribution with 1 degree of freedom. So we would reject Hardy-Weinberg if this number that we calculate is bigger than we would expect. And for example, we would say if it's bigger than 3.84, then what we see has only a 5% chance of occurring. And that's so small, we might say that we choose to reject Hardy-Weinberg. So just as there's a derivation of that variance formula here, we won't go into that, but there is an equation for the variance of the estimate, which depends on the parameter value, and under the hypothesis of f equal to 0, this reduces to 1 over n. Here's the chi-square distribution. The probability density, the area under the curve is 1. This is the probability density for the chi-square with 1 degree of freedom. It goes way off up to infinity at 0. But if we choose to reject for the most extreme 5% of the values, we reject when the number is bigger than 3.84. The chi-square bigger than 3.84 has a very small chance of occurring. So here's our rejection region. Now let's look at some data. So that's one way of approaching the test, a very explicit use of a maximum likelihood estimate. Sort of a more conventional test is to do goodness of fit. We've got 3 genotypes, 3 counts, and this is what we see in the data. If there's Hardy-Weinberg, what we would expect to see is the sample size times the square or the product of the allele sample frequencies. We compare the observed and expected numbers by constructing this little statistic, observed minus expected squared, divided by expected. And it turns out algebraically that this thing, in each case, for each genotype, is a function of the squared f hat. And adding those things up, we do indeed get sample size times f hat squared. So the chi-square goodness of fit statistic is exactly the same as regarding f hat as being normally distributed. So here's some data. Sample size 10, genotype count 6, 3, and 1. The sample allele frequencies are, for big A, it's the homozygote frequency plus half the heterozygote. So it's 0.6 plus a half of 0.3, 0.75. Small a, it's this homozygote 0.1 plus half of 0.3, we get 0.25. So squaring and product of those two numbers gives us the 3 expected, in quotes, expected genotype counts. And these are very close. to the observed counts. They're astonishingly close. And if we do the formal chi-square test by taking the difference and squaring it, dividing by expected, we get 0.4, which is a small number. And we would have got the same 0.4 had we have estimated F. The estimate turns out to be 1 minus heterozygote observed over heterozygote expected, 0.2, 0.2 squared, 0.04 times 10, 0.4. So this is way less than 3.84. We do not reject Hardy-Weinberg. It's a very small sample. And we can just check that things are correct. We put in there our command 3.84 with 1 degree of freedom. Now, where did the 1 degree of freedom come from? There are 3 genotypes, each with their data, but these 3 numbers add up to the sample size, so that reduces 1 degree of freedom. There's 2 degrees of freedom. And then we have used up another degree of freedom to estimate the allele probability. So we're left with 1 degree of freedom. Or what we might say is, how many of these expected numbers are we free to choose? The 3 numbers must add up to 10, and they must also add up so that we get the correct sample frequency. So this test, in fact, all the tests will look at are conditions on the sample allele frequency. There are 6 times 2, 12, plus 3, 15 over 20 of the alleles are capital A. And that's a constraint. The expected numbers must also satisfy that. Twice this number plus this number should also be 15, as it is. So we're left with 1 degree of freedom. And 3.84 is a cutoff value, 1 degree of freedom. The probability of being less than that number is 0.95, or more than that number is 0.15, just using a simple R command. Now, there's another number that we could have left out here, but this is 0. If the hypothesis is true, we have we invoke what we call the central chi-square, what we've just been doing. If in fact there is a departure from Hardy-Weinberg and F is not 0, the same quantity n times F squared, this is now the parameter, not the estimate. This product is called the non-centrality parameter. And these 3 things go together: the sample size, n, the degrees of freedom, 1, the significance level, 0.05, the level at which we would falsely reject. Those are all tied up together. And if we also want there to be a 90% chance of rejecting when F is not 0, then lambda has to be bigger than 10.5. So let's look at now the probability of a chi-square statistic bigger than 3.8, excuse me. Now, less than 3.84, 1 degree of freedom, and non-centrality 10.5. Instead of being 95%, we're down now to 10%. The probability of being bigger than 3.84, 1 degree of freedom, in lambda 10.5 is 90%. Conversely, if we start out with the 95%, what's the cutoff value with 1 degree of freedom? 95%, that's 95th quantile is the 3.84. If we want to cut off the bottom 10% when non-centrality is 10.5, we get 3.84. Here's the non-central chi-squared with 1 degree of freedom and non-centrality 10.5. We're going to set up our rejection region, our rejection rule, reject if the chi-square statistics bigger than 3.84. We set that up with the 5% criterion, the significance level. The probability of being bigger than 3.84 when the non-centrality parameter is 10.5, is this shaded area, 90%, 0.9. So the power and the significance level are all tied up together via this non-centrality parameter. These tests are not very powerful. If we want a 90% chance of detecting a 1% inbreeding, we need a sample size of 105,000. NF squared's got to be bigger than 10. If we're happy to have a 90% chance of detecting 10% inbreeding, then the sample size needs to be 1,000. Still a large sample size. So many of the sample sizes we use in our actual work are quite small. We're beginning to see data this size, but not very often yet. We're more typically in the size of a few hundred or a few thousand. So we're going to have low power for detecting Hardy-Weinberg for a single SNP. So significance level, 5%. Probability for false rejection, will reject when the hypothesis is true. The user specifies that. When we conduct that's our goal. We might not achieve that with an actual test, as we'll see in a minute. Once we've conducted the test, got the test statistic, compare it to the distribution, in this case with assuming chi-squared, the probability of seeing what we do, or something more extreme, is called the p-value. So a p-value of less than 5% is, sort of traditionally regarded as being significant. And we'll modify that in a minute. Now, this p-value, this probability of seeing what we do, or something more extreme, depends on the chi-square distribution, which in turn depends on the assumption of underlying normality of the allele frequencies. And we know that that's not correct, particularly as the allele frequencies get some distance away from zero. So these are, at best, these p-values are approximate if we're going to use the chi-square distribution. A better class of tests than the one we now use in practice are called exact tests, and the word exact means the p-values are calculated exactly. They depend on the binomial rather than the normal distribution. So let's go back to what we know about the data. Here are the three genotype counts, and we know that these are multinomially distributed. And it turns out that if we condition on the observed allele counts, and I'll just say that this is the probability of the genotypes given the allele counts, then that probability is this thing. It doesn't involve the allele probabilities, it involves only the data, the genotype counts, the number of heterozygotes here, and the allele counts. This is now our test statistic. That's very different looking than NF hat squared. But what our procedure is to say, let's reject Hardy-Weinberg if this probability is small. If it's not very likely, we'll see those genotype counts for those allele counts, if it's very small. And in particular, and by analogy to the chi-square test, by very small, we means the outcome we see belongs to the set of unusual outcomes. So it belongs to the set of small probabilities. So we need to clarify that. I've got a little derivation here. Let's not worry about that. Just to show you that this is the Hardy-Weinberg test. So here's a very simple example. 50 individuals, 49 are one homozygote, no heterozygotes, and one of the other homozygote. This is thought to be in Hardy-Weinberg equilibrium. It looks a bit strange because of 0 heterozygotes. On the other hand, these are small numbers, so we might not be too concerned. These data have 100 alleles, 50 individuals, 98 little a's, 2 big A's. And there's only two possible data sets. The one we saw, the 1049, and one more. This is the other set of genotype counts that have the same allele counts. And plugging in these numbers into the test statistic back here, we get these probabilities. So the data has just under a 1% chance of occurring under Hardy-Weinberg. The one we didn't see has a 98% chance, 99% chance. So the probability of seeing what we did, or something more extreme, is 1/99, 1%. So it's not very likely we might choose to reject Hardy-Weinberg with that outcome. The thing that underlines this exact test is a calculation for the data at hand and some account taken of the probabilities for all the other possible data sets. And just now, if we had have done the chi-square test, the chi-square test statistic would have been 50, and the probability of the chi-square probability of that is 10 to the minus 12, which was a lot different from the 0.01 that we know is correct. So just showing that the very low allele frequencies, the chi-square normal distribution is not really appropriate. So slightly more realistic, the example we looked at a few minutes ago, sample size 10, genotype counts 6, 3, and 1. The allele counts were 15 and 5. The probability of the data was 0.43, quite high, certainly a long way from 0.05. There are now two other data sets, fewer heterozygotes or more. These are the only three possible genotype sets with those allele counts. Their probabilities are one which is a bit under 5% and one which is 50%. So if we have a sample size 10 and the allele counts were 15 and 5, we would reject for 7, 1, and 2. We would not reject for these other two data sets. So the target or the nominal significance level was 5%, and in fact, false rejections will occur very close to that. Now, getting a more realistic, still sample size 100 and a minor allele count of 14 alleles, frequency of 7. Allele frequency of 7, 200 alleles, 14 capital, 14 little a's. There are, looks like half a dozen, 8 different possible sets of genotype counts that have 14 small a's, ranging from 7 homozygotes, no heterozygotes, up to 14 heterozygotes. Here are their 8 outcomes. Here are their probabilities using that equation with all the factorials in them. Here are the chi-square test statistics. So for each of these outcomes. So the chi-square test would say we would reject Hardy-Weinberg from here on up, because the p-value of getting 5.38 is 2%, and all the other ones are even smaller. So this is the cutoff. 10 or fewer heterozygotes cause rejection. The exact test, however, here are the probabilities for each outcome. The p-value is the probability of the outcome plus the smaller values. So 0.0051 for this outcome, and add that to the smaller numbers, and we get 0.0053. So now this is still less than 5%, so we would reject here. So the exact test says reject for 8 or fewer heterozygotes. If we get up to 10, the exact p-value is 6%. So it's just above the arbitrary threshold of 5%. Now, the nominal significance level is 5%. The actual significance level for the exact test is 0.5%. and it's 2% for the chi-square. So that's the test, the exact test. There's we're going to make one modification. So for the exact test, the usual way is to define the p-values, the probability of the data, plus the probabilities of all the less likely data sets if there's hardly one bit. It turns out that when you do that, we don't quite get the correct procedure. Now, there's some theory which says, for example, that if you test a lot of hypotheses and they're all true, you do all these various tests, there'll be a range of outcomes, of course. You'll get with many samples, you get a range of test statistics, and the p-values that we calculate for a large number of true hypotheses will be spread out uniformly between 0 and 1. If you look at the p-values for a set of exact tests, we always get a spike at a p-value of 1. And if you think about it, let's go back to like this. There is always one outcome, one probability of one genotype set, which has the most likely, and its p-value will be 1. So if we do a lot of tests, we're always going to find an outcome with a p-value of 1. So instead of getting the p-values spread out uniformly for a lot of tests, we're going to get in excess of values of 1. This was noticed by our colleague Jan Graffelman and another guy Marino, and they said it's actually better to modify the way we calculate p-values. Let's take the probability of the data and divide that by 2. So take half of the probability of the data and add to that all the smaller probabilities. So here's a histogram of p-values for a population in Hardy-Weinberg equilibrium. The usual way is to look at the probabilities of each outcome and add up the most extreme 5%. And there's this is plotted against heterozygote numbers. There are some heterozygotes which are less likely than we would expect under Hardy-Weinberg, some which are more, and together the rejection region would be the heterozygosities corresponding to those 4 values there. The mid p-value that Graffelman advocates is to take half of the probability of the data. If the data set was 13 heterozygotes, take half of that and add together the smaller numbers. This mid p-value correction is a function, is an option in Plink. Does it have much of an effect? It can do. So let's look at the 631 example. Here are the probabilities. The usual p-value for this outcome is this data plus the smaller number, 0.48. And for this outcome, it's this number plus those ones, p-value 1. The mid p-value says let's take half of the data probability, 0.26, and add it to those 2 numbers, 0.74. So now we no longer will have a spike at p equals 1. We'll get them more spread out, and we'll get closer to an average p-value of a half with this correction. So looking back at the sample size 100 with 14 minor alleles, here are the probabilities. The mid p-values are now half of each number plus the smaller numbers. So, and now we end up with something which is much closer to the chi-square test, and with the same rejection region, reject 10 or fewer. The nominal significance level was 5%. The actual significance level with the exact test is 3.5%. So we would certainly say, if you want to test for Hardy-Weinberg, use the exact test with the mid p-value correction. Here's a plot from Graffelman's paper. The top 3 panels are for sample size 100, quite small. bottom panel for sample sizes 1,000, maybe more realistic, plotted against the minor allele count. So the extreme values of minor allele frequency of a half. The green numbers are the mid p-values. Now, the black line is 0.05. So the nominal p-value is 0.05. We will decide to reject based on that desired significance level. We never actually achieve that until we get out with the allele frequencies close to a half. So here's the mid p-value, and then the other numbers are for the exact test using the conventional p-values. Anyway, they're up and down. The very bizarre behavior. So when we conduct the test, we're aiming for 5%. The actual significance level we have can be more or less than 5% for small minor allele counts. So these tests, these are the best we have, but they still have some strange behavior, and we should be aware of that. We saw for the chi-square test how to think about power with the non-centrality parameter. I'll just say that we can also calculate power for the exact test. Instead of working with the non-centrality parameter NF hat squared, we work with another quantity, which is the heterozygote divided by the square root of the product of homozygotes, like a harmonic mean. It's a strange looking measure. It's another way of measuring departures from Hardy-Weinberg. These are the probabilities. If there's Hardy-Weinberg, this top line is 2PA, P little a. The bottom line is PA, P little a. So psi equals 2 when there's Hardy-Weinberg. A bigger value than 2 is an excess of heterozygotes. A smaller value than 2 is an excess of homozygotes. And there's some algebra there, which I don't think we need to do. So let's look at our small sample. Here's our 631 data set. This column is the probability of the data when there's Hardy-Weinberg, this is psi equals 2. Here's the probability of the data if the inbreeding coefficient with the partial Hardy-Weinberg is quantified by a psi of 1. There's an excess of homozygotes. So we look at this column. This tells us when to reject to give 5% significance, and this says reject when we see 712. This says if that's our rejection region, and we get this outcome, the probability of what we see is 37. So it's a 37% chance of rejection. So the power is 37% for this outcome. The power for this outcome is 36%, and so forth. So now here's a more extensive table, sample size 100, where there are 16 copies of the minor allele. The number of heterozygotes possible for 16 minor alleles goes from 0 to 16. Here are all the possible outcomes. These are all the possible data sets, just shown by the number of heterozygotes. The middle column is the probability of each outcome. And these are the probabilities, and the line is the rejection regions. Anything above the line causes rejection because the p-values are all less than 0.05. As the number of heterozygotes gets smaller, the number of homozygotes gets bigger, the inbreeding coefficient gets bigger, psi gets smaller. So all this probability mass down here sort of migrates up in this direction. So as we get further away from Hardy-Weinberg in the direction of more homozygotes, there's a bigger chance of rejecting. It goes from 1% initially, it goes up to 99%. by the time we get to 63% inbreeding. So that seems to be, that shows us the power as the inbreeding level, departure level departs. In the other direction, it's a bit strange because as we get smaller inbreeding coefficients, ones less than 0, or bigger values of that quantity psi, we get the probability of mass going even further down to the bottom right-hand corner. So there's actually becomes a smaller and smaller chance of rejecting. The power actually goes down as we get a bigger departure from Hardy-Weinberg in the direction of more heterozygotes. And from the Graffelman paper, he's just plotted power. This is the plots for when there is Hardy-Weinberg, and these are the plots for departures from Hardy-Weinberg. All right, so how are we doing? So, 2 ways of testing for Hardy-Weinberg. One with the simple-minded chi-squared or goodness of fit test, based on underlying normality of allele probabilities. Then a better exact test, a little bit more computational, but certainly for SNP arrays, SNP data, not too much, because the number of possible outcomes we have to consider is really it's about half the sample size. And the number of possible heterozygotes is about half the sample size. So it's quite computationally feasible. If we have microsatellites, multiple alleles, things are extremely difficult because there are too many data sets. Let's go back to this example. So there's only the number of alleles is 16, and there's only half that number, more or less, of possible data sets. For multiple alleles, those are with multiple alleles, the number of possible data sets is enormous, and it's computationally not feasible to do a complete enumeration. So what's done instead, and we'll see an example of this later on in the module, is a so-called permutation test. So instead of a complete enumeration like this, which involves computation for each outcome, we have to do the complete enumeration. We need their probabilities, we need to rank them, and we need to look for the cutoff. Instead of that, it's not too bad for SNPs, but for multiple allele loci, too much. We look at just a random set of the outcomes. Instead of all of them, we just look at a random set, and we get that random set by permuting the alleles. So here we've got 200 alleles, 100 individuals, 200 alleles, some A's and some little a's, but they have a particular order. They occur in pairs for the data, the genotypes. But then we just shuffle that to those 200 alleles to generate a new set of 100 genotypes. And for each of the shuffled or each of the permuted sets of alleles, we recalculate the test statistic and get a distribution of the test statistic for that random set, and see if our data value has an outcome that belongs to that most extreme data set, that belongs to the most extreme outcomes. And we would typically do a few thousand, maybe 10,000 permutations. So that's permutation testing. That's a very powerful technique. Maybe not necessary for SNPs, but still it is done often in practice, particularly when the sample sizes get to be up in the millions. Now, if we have 1 million SNPs, that's 1 million Hardy-Weinberg tests, and we very often do that many tests or more in cleaning data. So if we're going to tolerate a 5% significance level, that means we're going to be falsely rejecting 50,000 times, and that might be thought to be extreme. So instead of maintaining the 5% for every test, we adjust the significance level for each individual test to give us an overall 5%. So overall, over the whole collection, let's suppose it's 5% false rejections expected. So if overall a rejection is at least one rejection among the million SNPs, or in other words, 1 minus no rejections, and each test individually has a chance of not rejecting falsely 1 minus alpha prime for the individual test. So take 1 minus alpha prime, the number I'm looking for, to the power of the number of tests if they were all independent, subtracted from 1, that should give me my target or experiment-wise. So this is approximately the number of tests times the individual test significance level. So each test individually would be tested at the overall level divided by the number of tests. So that's called the Bonferroni correction. It's extremely conservative. It's given rise to what's often called in the human genetics literature the genome-wide significance level, as though there were a million tests and as though 5% was a magic number. So if you divide 5% by a million, you get 5 times 10 to the minus 8. And that's sort of become an industry standard. It's completely ad hoc. The 5% itself is not magic. And some studies have more than 1 million SNPs, some have less. And then the tests are not independent. So there's a lot of reasons not to adopt this too seriously, but it's often reported and many journals expect to see it. A better way of thinking about multiple testing, instead of just blindly applying Bonferroni, is to do what's called a QQ plot. Let's conduct a series of tests. It might be a data cleaning where we've got 1 million SNPs, 1 million tests. And let's ask the question, are some of those tests really significant? Some of them not. So let's get our 1 million p-values, or mid p-values, or chi-squared p-values. However we do the test, we get some p-values. And then if we were willing to believe that if all the hypotheses were correct, were true, then those 1 million p-values would be spread out uniformly between 0 and 1. So that's the assumption. So we get our 1 million actual p-values and rank them from smallest to largest, and plot these 1 million values, these 1 million ranks, against the ranks we would expect for 1 million tests. So on the x-axis, we have the expected p-values. So it's just a matter of dividing the range 0 to 1 into 1 million pieces. So lots of ways of doing that. We might say the smallest value is 1 over 2n, all the way up to 1 in the number of tests. So a half of that, and then 3 halves, 5 halves, and so forth. So we've divided the unit interval into 1 million pieces on the x-axis. On the y-axis, we plug and put in the observed ranked p-values. Because we're interested in the significant values, we're really only interested in the very small values. So what we do is transform the p's to minus log 10p. So a p-value of 0.01 becomes 10. Example, becomes 100. A p-value of 1 becomes log 10 is 0. P-value of 0.1 is p-value is 10, and so forth. So as a QQ plot, and then these are often described by a thing called the genomic control quantity. And that's also written as lambda, unfortunately, but it says let's take the median of the observed p-values divided by the median of the expected values, which the expected value median is a half. We'll take the median of the observed p-values divided by the median of a half. And if everything is as it should be, this ratio should be 1. So here's a QQ plot on the log minus log 10 scale. So a value of 1 corresponds to minus log of 0.1, minus log of 0.2, minus log of 0.01, minus log 0.001, minus log 0.0001. This is a test on a series of 9,000 steps, and you have these data. They're published. It's a nice classic data set of macular degeneration in humans. 50 people were typed who were controls for the disease, and then some other people with the disease were typed. Here are the 50 controls, and there's 9,000 tests, and these are the exact test p-values. The observed values versus the expected, as though the 9,000 is spread out uniformly. That's on the log 10 scale. And if everything was fine, that all the points were lying on the red line, the line of equality. So when we start to get departures, these SNPs here have p-values which are smaller than expected for that many tests. Smaller p-values, bigger minus log 10 p-values. So this is quite a large number of SNPs which appear to be really departing from Hardy-Weinberg. And the point of departure is round about minus log 10p of 2, p-value about 0.01. So it's a long way, it's a lot different from the Bonferroni correction of 5% divided by the number of tests, which is 10 to the minus 6. So Bonferroni would say only reject if we're out here somewhere. So we'd maybe only reject for those ones. So, and this is not unusual to find a QQ plot like this, where the departures from equality tend to happen around 2 or 3. At this data set, we noticed something though, and we noticed that there was quite a bit of missing data. Several of the SNPs were not typed in the whole 50 individuals. So now if we only look at the SNPs for which the whole 50 individuals were typed and redo the QQ plot, we get quite a different story. Now we see only 5 SNPs which appear really to depart from Hardy-Weinberg. So instead of 9,000 SNPs, it's only 7,400. Turns out that this is sort of, now we can look at these 5, and it turns out they're pretty obviously out of Hardy-Weinberg because the sample size is 50. In this case, they all had at least 32 heterozygotes. So the allele frequency was at least 32 over 100.3. But there were 0 homozygotes for the minor allele. So the allele frequency is at least 0.32, but there were no homozygotes. So that's very odd. So something's gone wrong with the genotyping. Graffelman's also thought about this problem. He said, well, it would be wasteful to throw away SNPs if there was incomplete data. And one way around that issue is to impute the missing data. This is a little bit different from imputing untyped SNPs, where we might have a SNP array of a million SNPs, and we want to impute all the SNPs from a whole genome sequence study. So we would use the data from the whole genome array to impute these SNPs that were not typed in our study. This is a little bit different. We just have a single sample, and we use the data itself, the data from that study, use neighboring SNPs to fill in the alleles which are missing. for some of the SNPs. And there's standard packages that will do this. So Jerome showed this plot in the last practical. This is so-called ternary plot. So it's each SNP is represented in this triangle, and the three vertices are where the SNP is particular genotype. So in the middle, we've got the frequency in the whole data set. Only homozygote, only homozygote, only heterozygote, and otherwise we take the distance from each point to the line as the frequency of the genotype in the opposite vertex. Hardy-Weinberg corresponds to SNPs who fall on this parabola, and they mainly do if the data are complete, no missing data. If we've got 5% missing, that's 5% of the SNPs are not typed on every individual, then we get a lot of departures, a lot of apparent departures. And that has to do with acting as though the sample size was the same for every SNP, but it's clearly not. The 1,000 genomes data we're looking at in the course is complete. There are no missing data, so we don't have this issue. In practice, of course, missing data is a huge problem. These data that Graham was looking at were from SNP array data, where the genotype calling was based on basically on the amount of DNA from each of the alleles. We got signals from the two alleles we've got, and these are plotted in a two-dimensional plot, basically representing the amount of DNA from the B allele on the x-axis and from the A allele on the y-axis. So here we've got individuals which are B alleles missing. These are homozygotes for A. Here the A allele is missing, homozygotes for B. Here are the genotypes, the heterozygotes. And here is the missing data. These are individuals that are not typed, of which there's no signal. And here's a missing observation. So this is a good SNP. There's not much missing data. Here's one with a lot of missing data. There and there and there. So what if we choose to throw away the SNPs with any missing data, then the p-value is 0. In this case, here the p-value is still significant. If we discard the SNPs that have any missing data, but if we do some imputation, then it's rescued, if you like, here and here, and here goes the opposite way. So it's complex, I think. Hardy-Weinberg testing, it's not for the faint-hearted when we do large-scale studies. There are things that can go wrong, and we have to watch very carefully. The other thing, of course, is that we need to be very careful constructing the QQ plots, because not only do these assume that the p-values are uniform, which is not strictly correct even with the mid p-value for the exact test. They also assume it's the same distribution for every SNP, all the sample sizes are the same. And it also assumes, basically, it ignores this bizarre behavior. So it's clearly the same distribution doesn't hold for every SNP. It depends on the number of copies of the allele. So the QQ plots are a good way of thinking about multiple testing, but we do have to be aware that it might not be straightforward. So many of us work with data from species with two sexes, and where one of the sexes has 2 copies of the sex chromosome, the other has only 1. So in humans, we've got females homozygous for the X chromosome and males 1X and 1Y. How would we test for Hardy-Weinberg for X-linked markers on the X chromosome? So usually we use, well, can only do that. It's only a sensible question if we look at the females, where those are the only individuals with 2 copies of the local genes. So X-linked Hardy-Weinberg tests are generally done only on females. It does throw away half the individuals in a typical study, however, and it throws away information about the allele frequencies in the data in the population. If there is Hardy-Weinberg, the allele frequency should be the same in males and females. So to throw away the males, we're throwing away some information. So what Gravelman suggested is that we do a single test, which takes into account both the males and the females. So here's a test statistic. We've got NF males, I've got NF females in the data set. The males have MA and MAA copies of an X allele, of an allele at the X locus, one of the X loci. The females, these are the counts for the alleles. The female, well, these are also actually, of course, the male genotype counts, as they've only got single alleles. Here are the female genotype counts. Here are the number of A alleles, little a alleles in the whole data set, and number of males and females. And here are the number of heterozygotes in the females. So that's the test statistic. So we calculate that, and if that is small, we would reject Hardy-Weinberg, and this is affected both by departures of Hardy-Weinberg in the females and by differences of allele frequencies in males and females. So here's a situation where there are 6 capital A alleles. The data set has 10 males and 10 females. Here are all the possible sets of data, and here are their ranked probabilities. So we say, well, if I'm amongst these values, then I would reject Hardy-Weinberg, take it into account possible male-female allele frequency differences. And you can look at this plot slowly, but it makes a difference whether you test only in females or test in both. We would suggest thinking about testing in both. And then there's some more details on that. There's no reason to stop with X chromosome. Once we've taken that slippery slope, if you like, taking males and females into account, we can extend that thinking to testing for Hardy-Weinberg in general. So we generally test for Hardy-Weinberg using all the data we have for autosomal loci. Just simply combine males and females. Of course, that assumes that each of them separately are in Hardy-Weinberg equilibrium. And it also assumes that the allele frequencies in males and females are the same. And there's sort of a vicious circle. We should check that. We should check that the male and female frequencies are the same. But the test, we do assume Hardy-Weinberg in each. So let's test for Hardy-Weinberg in each. But the test, we do assume equal allele frequencies. So there's sort of a vicious circle. And there are all kinds of things that can go wrong. The 2 sexes might have equal allele frequencies and both in Hardy-Weinberg. They may have different allele frequencies and Hardy-Weinberg. They may have the same allele frequencies, but not in Hardy-Weinberg. And just all these possible scenarios. And Gravelman has come up with this sort of omnibus statistic. It's a function. It looks somewhat familiar, somewhat like the exact test for Hardy-Weinberg we saw at the beginning, but it takes into account all the data, keeping track of which data are from males and which are from females. Here's an overall test. It has 2 degrees of freedom. It's sort of equivalent to a chi-square at 2 degrees of freedom. It's an exact test. So we calculate this for the data at hand, and then we need to decide if that's a small number or not. So we'd have to examine all possible data sets or do some permutations. Is this a small number? If it is, then we would call into question 2 explanations. It's small if the data is unlikely, either because there's hardly one big departure, or because the allele frequencies are different in males and females. And of course, those 2 things are interrelated. All right, so this is just more details on that. And then I think just near the end, so when we start looking in great detail at results of whole genome scans, we find very interesting patterns. So the MHC region, where the HLA genes are, is very complicated, very much affected by natural selection. So here's the MHC region, SNPs over this 4 megabase region, and here are the log 10 p-values just plotted along the chromosome. There are 3 spikes where things are clearly different, where there's clearly significant departures from hardly one equilibrium. And then sort of zooming in just in a narrow region around the HLA gene, then we see a complicated pattern of departures from hardly one, but the green points are where there's significant hardly one disequilibrium because of the excess of homozygotes, heterozygote deficiency. The red values are significant because there's an excess of heterozygotes. So very complex patterns. It's not usual to concentrate on the MHC region with population genetic studies. And then just a couple of minutes, I think we've got 2 or 3 minutes, but that's all. This was disequilibrium. It was a statement about 2 alleles at a single locus, single SNP, for example, carried by individuals. Does an individual carry a pair of SNPs which seem to be associated in some sense? Is their joint frequency different from the product of their individual frequencies? We can extend that to pairs of alleles, one from each of 2 different loci. And if we had data from gametes, we call that gametic linkage disequilibrium. If we don't have phased data, then we can do something about 2 loci just from genotype data. So just a review of the notation. This is for a gamete, a haplotype. These 2 alleles, A and B, are received by an individual from a single parent. How often do they occur? What's the probability they occur together, those 2 alleles? We compare that to how often we would expect them if the alleles were not associated, they were independent. This measure is called the linkage disequilibrium parameter. Here's 100 chromosomes, 100 haplotypes. There's a marker, YFM, that's going to be in plus or minus alleles, 25-75 split. And here's a disease-causing locus where the A allele results in the disease, the N is the normal. So this complete association, all the chromosomes carry the A allele at marker type plus. So the linkage disequilibrium has its maximum possible biological value, although the actual LD parameter is very small. This is very small. And we can do some algebra if we wish. The disequilibrium parameter is the covariance of the indicators for alleles at two different loci. And the usual statistic is the correlation, the D divided by the square root of the product of allele probabilities. This correlation is this R, or the square R squared, is actually the correlation of the allelic states at two different loci. If we have data from gametes, we can get the observed proportion of haplotypes or gametes minus the product of the sample values. That's our test, that's our disequilibrium. The sample correlation is this thing. R squared is the square of that, and NR squared is a chi-square distribution, has a chi-square distribution. So this correlation coefficient plays the role of two loci that inbreeding does for one locus. And I think that's about all I need to do here. There's some work on genotype-based ignore. Another way of measuring it is to work with genotypes and take the allele dosages for each individual. The A locus has a dosage 0, 1, or 2, but the B locus is a dosage 0, 1, or 2. The correlation of those two dosages is twice this measure that we're calling the composite linkage disequilibrium. It's a measure of LD, but based on genotypes. And if we square the correlation, this is the covariance, if we square the correlation of the X's times the sample size, we get something very like a chi-square test of this thing. And I'm going to just show you a plot of the behavior of that squared correlation of dosages as a function of the distance apart. So as the SNPs get further apart, their squared correlation diminishes. So this is an observation to the 1,000 genomes data, two different populations. And this is the basis for association mapping. If we see evidence for linkage disequilibrium, we take that as evidence for small distance between the two quantities. If the disequilibrium is between disease status and marker type, we work our way through the logic. If we use an LD type measure, we're getting a surrogate for distance. So that's just the observation. And I think we should stop. We're just a little bit over, so let me stop sharing and stop recording.